Hello. We are going to be learning about normal distributions and probability today. And this is the second time I'm recording this video because the first time deleted itself after I finished filming it in 25 minutes. So let's see if we can get this done in 20 now that I've had practice doing it. All right, so we're going to start off with just a quick little review about what standard deviation is. Okay, so just as a reminder, the standard deviation of a data set measures the average distance a number is from the mean, right? So the average distance a number is from the mean. So that tells us that if a standard deviation is really small, it means most of the numbers are kind of close to the mean. If a standard deviation is really large, then it means that the numbers are maybe a little bit farther away from the mean. So you have a warm-up question here, 2 of them actually, so you should pause the video now and you should try to answer these 2 questions on your own. Did you pause the video? You totally did, right? You wouldn't lie to me and say that you paused it when you really didn't, right? You did. I believe you. You totally did. All right, compare the mean and standard deviation of the 2 data sets. So let's start off with data set A. When we're looking at this guy here, it looks like it is pretty normally distributed, so it's a very symmetric graph. And we know that the mean is going to be at the center when it's normally distributed or symmetric like this graph is. So we can say that the mean of data set A is going to equal 15. And as far as its standard deviation, we could try to do our little estimate and try to figure out like exactly how far that is. Like, you know, to me, that's like 1.5 maybe, but I think we'll just keep it as a comparison between the 2. And we're just going to say that this one is definitely smaller than data set B because it's very close to that mean. You see how high up it goes at A? That's because all of the data is really focused around the mean, and the closer it is to the mean, the smaller the standard deviation will be. For data set B, when we're looking at this guy, right, it's going to have a mean that is approximately 12. And if we try to do our little shortcut thingy here, it's probably going to be somewhere around like 4-ish. But again, we're going to focus on the fact that it is much larger than the standard deviation of A because it's much more spread out, right? So our data is much further away from the mean than it is in A. All right, if we have block here, oh, I was going to try to read the whole thing off of memory. That failed miserably. I only did it one time, you know. All right, 2 different algebra 2 blocks. One meets block 5, one meets block 6. They both take the same quest. The class that meets block 5 has a standard deviation of 10 in their scores, while block 6 has a standard deviation of 20. What can we tell about the differences in these? And all we can really tell about these 2 things is that block 5 was more consistent in their scores, right? Smaller standard deviation means that they were much closer to the mean. And that's about it though. We have no idea if block 5 did better than block 6 or who did worse, who did better, who did they do the same. All we know is that block 5 was more consistent because their standard deviation was a 10. That means like block 5 could have had a mean of like 40, and that means that all of their scores were between a 30 and a 50, right? 10 on either side is about average. Whereas block 6 maybe had a standard deviation of 20, but it was at a mean of 80, and so its scores were roughly between 60 and 100, and so therefore block 6 did better than block 5, but block 5 is just consistently low, whereas block 6 was more inconsistently high. So what we see from this example is that we need a better way to compare 2 data sets, all right? And the way that we're going to do that is with something called a standard score, or the z-score, okay, a standardized score. And what this does is it allows us to calculate a new score that is standardized, that then we can compare these 2 scores to each other and be able to say like, oh, look, they have a similar z-score. That means that they are similar to each other. Or, oh, wow, these z-scores are very different. And so we can tell that this did better than this other one, you know, if we were whatever we're looking for. So it's a very simple formula. To find the z-score, we do the value that we're looking for, so an individual data set value, minus the mean divided by the standard deviation. In symbols, we use x for the value, and for samples, we do x bar over s, If we were in populations, we would do mu over the lowercase sigma to represent the population mean and standard deviation, as opposed to the sample mean and sample standard deviation. So remember, Greek letters are population, normal letters, our letters that we use, are going to be for samples. We have a little thought-provoking question for you. If you found out your z-score from the recent tests, would you want it to be positive or negative, and why do you think that? So take a second, literally like one Mississippi. All right. What do you think? Positive, negative? Did you all just shout out positive, like we're watching like Dora the Explorer or something, and then I get to be like, that's right, positive? No? Okay. Well, we want it to be positive. And if we stop and think about it, it kind of makes sense because our value goes right there. And so if we are doing a value minus the mean, if our value is bigger than the mean when we do this subtraction, our number will be positive. If our value was less than the mean, then the number would be negative. And so if we're talking about an exam score, we definitely want to be above the mean. And so we would want to make sure that our z-score was positive because that means that we are above the mean. Make sense? All right. An example. On an Algebra 2 benchmark exam, had an average of 80 with a standard deviation of 10, and we want to find the following z-scores of all of these cool people. All right, so we first, let's say we got our mean of 80, and our standard deviation is going to be 10, and we know that the z-score formula is x minus the mean over the standard deviation. So, Dr. Gundel, I wonder who that person is. Sounds cool. Z equals our score of a 92 minus 80 over 10. All right, 92. Dude, this Dr. G must be super smart or something. That equals a z-score of 1.2. Mr. Robinson, had a bad day. 75 on their score. So we're going to do 75 minus 80 divided by 10. That's going to give us a z-score of a negative 0.5. So see how the score was less than the mean. So our z-score was negative, whereas Dr. G's was above the mean, so positive. All right, now we got Miss Baskey. Got directly equal to the mean. So that's going to be a z-score of 0. So if you're equal to the mean, your z-score is 0. If you're better than the mean, positive. Less than the mean, negative. And last but not least, we got an 86 out of 80. That's going to be a 0.6. All right, so now you can see how the further away from 0 we are, the more positive we are, the higher, the further from the mean we are. So 92 is a z-score of 1.2, pretty far away from the mean. A z-score of 0.6 correlates to an 86, so both positive. And now we could do comparisons and say like, hey, if you had a z-score of 1.2 and a z-score of 0.6, then we know that a score of 92 is better than a score of 86. And ultimately, we'll be able to do this with different data sets and be able to say like a student who's in Dr. G's class got a z-score of 1.2 versus a student in Mr. Robinson's class got a z-score of negative 0.5. We can now say that the student in Dr. G's did better than the student in Mr. Robinson's compared to their class, okay? So it is still a comparison to their individual class, and that's something we've got to kind of keep in mind, but it's a way that we can start comparing. All right, let's keep going with this. We're cruising, we're having so much fun, I can tell. If the test was out of 100 points, what is the maximum possible z-score and what is the minimum? So if we were to do the maximum of 100, so 100 minus 80 over 10, that's a max z-score of 2. I'm going to try to do my 2's like the fancy 2's because they look like z's otherwise. And our lower score, well, that would be a 0. So we would do 0 minus 80 over 10, and that would equal negative 8. And we're going to learn this when we flip to the next page, but a z-score of negative 8 is basically unheard of. It's basically impossible to happen. So that would be really unexpected for someone to get a 0 when everyone else in the class was averaging 80 with a standard deviation of 10. All right, we got 2 more questions here, which are kind of working backwards. We say, hey, this z-score was 0.8. What was the actual score? So we say, hey, if the z-score was 0.8, we want to find out what our x value is. Right? So I'm going to cross multiply the 10 to the other side. So I'm going to get 8 equals x minus 80. And so x will equal 88. All right, now Luke, off day for Luke, negative 1.5. So we're going to have 1.5 equals x minus 80 over 10. Multiply that 10 to the other side. We're going to get negative 15 equals x minus 80. Add the 80, and we get x equals 65. Okay? So positive z-score above the mean, negative z-score below the mean. Really can't emphasize enough that that's like the quick and easiest way to tell you something when just looking at a z-score or trying to find a z-score. All right, now we get to the big stuff, the empirical rule. So when we're looking at this giant normal distribution, first thing we have is right down the center here, this is where the mean goes, right? We know that the mean is chilling right here. And we just figured out that a z-score of 0 is going to be equivalent to the mean. Now, what these little tick marks we're talking about down here are little standard deviations. It's saying, hey, when you're 1 standard deviation away, 2 standard deviations away, 3 standard deviations away, and then we can go backwards as well. So negative 1, negative 2, negative 3. And in a normal distribution, it kind of makes this little curve, right? We talked about that in the shapes in the last lesson. And we know that there's 100% of the data is covered by this thing. So if I just went like all the way across, 100%, taking up everything. And what that means is that if we break it down the middle, there's 50% of the data is that side and 50% of the data is on that side. All right. Now that we kind of have that down, which I hope that kind of makes sense, right? The graph is perfectly symmetrical and there's 100% total, 50% is going to be on either side. We get to what this thing called the empirical rule is, which is less important nowadays with modern technology, but back in the day was way more important. And the first thing it says is that 68% of all data is within 1 standard deviation of the mean. And that means in both directions. Okay, so if we were to highlight this, which I don't want you to highlight this, so if you're trying to highlight, don't, because I'm going to erase everything that I'm doing right now. But I guess I could leave it there. You know what? I'll leave it there. That's 68% of the data is right there. All right, that means that there's 32% that's on the outside. I don't know if I did that math right. I'm like, whew. Yeah, 32% that's on the outside on either direction, left or right of that, and 68 here in the middle. All right, so 68% going that way, and we know that there is 34 going in either direction then, because the graph is perfectly symmetrical. So I'm going to actually add that way down here, and I'm going to say, hey, there's 34% going this way and 34% going this way, and 68% within the 1. All right, next what we got is 95% of all data is within 2 standard deviations of the mean. Okay, so if we were to do this, I picked terrible colors for the highlighting that's about to happen, but if we were to do this little yellow bit right here all the way across to this part here, and unfortunately it's going to make green, and there's no real way for me to get around that at this point, but you know, this whole section here, everything included, so the yellow plus the blue, that's going to be 95%. Okay, so let me try to find a way of drawing that without like just ruining this entire thing here. So this is 95%. Now, again, the graph is symmetrical. So if we take 95% and cut it in half, we're going to have 47% is going to be on the left side of this line in the middle, and 47.5% is going to be on the right side of the line. And if there's already 34% there, then we can actually say, hey, then just this little sliver between 1 and 2 is 13.5, and the graph is symmetrical, so it'll be the same thing. So if we add 34 and 13.5, that's going to add to 47.5, and if we add 47.5, 47.5, 95% for the total amount. Whew, making any sense whatsoever? I have no idea. I'm just going to hope so. All right, last one we got is within 3. So if we now add let's see, this red section, the yellow section, and the blue section with the random green that I highlighted in there for whatever reason, that value is going to be 99.7% of all data is within 3 standard deviations of the mean, okay? And so, how am I going to draw that without it being a mess? Whew. All right, there we go. We kind of got it, 99.7%. Same idea as we did before. We can take this value, we can cut it in half, and we'll get whatever that is. I can't do 99.7 in my head. And then we can subtract the 34 and subtract the 13.5, and we're going to get that this little sliver here between the 2 and the 3 is 2.35% on both sides here, 2.35%. And then last what we have is if 99.7 goes from -3 to 3, then that means that there's 0.3 that's left over on the outsides of the -3 and the 3. And if we split that up evenly, we're going to have 0.15% on either side that is chilling outside of the 3 or the -3. And that's why when I said, hey, a z-score of -8 would be almost unheard of, because here's -3. So -8 is like way far down, and there's already only a 0.15% chance of being less than -3. So getting to -8 is just like not happening. All right, so now that we have this, let's talk about what you need to know or not need to know. So first of all, next class we're learning how to do all of this on the calculator. And so I think you would have your calculator on any sort of test or quiz or final or anything that would involve this specific amount. Z-scores, maybe not. Probably wouldn't have a calculator for them. The numbers would be nice. You could probably figure it out. This stuff, probably have your calculator. But let's pretend like you didn't for a second. There's 2 ways that you can memorize this. The first way is to memorize the 68, 95, and the 99.7. Back in the day, we used to remember it by phone numbers because phone numbers have 7 digits, not counting the area code. And so we would say like 689-5997. And that's how we would remember it, because we were old and we had to memorize our phone numbers because we didn't have a phone that would save it for us. So that's one way. 3 numbers memorized, and then you can basically build everything that I've already built here. The other way is to memorize these numbers that I've been writing on the bottom. So 34, 13.5, 2.35, and 0.15, which is 4 numbers, but they're 4 more complicated numbers. So it's 1 more number, and they're a little bit harder to memorize, but they actually make everything easier for you to solve. So it's really up to you. I'm going to explain everything from the 68, 95, and 99.7 because that's how I was taught to do it. But I'll also mention how you could do it other ways. All right? So let's use these things so we can see what we're talking about before we get to some actual word problems. So we want to find the percent of the data that is over 1 standard deviation above the mean. So we have a little tiny thing here. Here's our 1. And we're asking, what is this part all the way here? Okay, so if I was doing this, what I would say is, hey, from here all the way till forever is 50%. And then I know that within 1 standard deviation of the mean is 68%. And if I cut that in half, that's going to be 34. So this part right here that's in green is 34%. So if I did 50 minus 34, that's going to tell me what this leftover bit is, right? So this part is 50, the total bit, minus the 34, the part in the beginning I don't want to count. And that's going to give me 16%. So I know that there's 16% that is above 1 standard deviation above the mean. Another way of doing this is to focus on the 68 again. You can say, hey, there's 68% that is within 1 standard deviation. That means that there's 32% that's outside. So I just did 100% minus 68%, and I would get that there's 32% outside, but that's in both directions. So then what I want to do is divide that in half to give me just one side. And so that's where I get the 16. There's 16 on the low side, and there's 16 on the high side. Okay? And there you go. That's one way of figuring it out. The other way is you can just look up here and you can say, hey, I'm going to add 13.5 plus 2.35 plus 0.15. And what do you know? That adds to 16. And that way, that works fine. You want to do it that way. It all depends on which way you have things memorized. All right? I think you'll find my way is a little bit faster than adding all those up, actually. But, I mean, maybe that's just me being biased because it's how I learned. All right? So here's -1. Here's 2. That's what we're trying to go between. I'm going to mark off this in the middle here. And I'm going to say, hey, this part right here, that's half of 68 because it's 1/2 of the within 1 standard deviations. This part over here is going 2, but it's also only 1/2. So I'm going to do half of 95. So I do half of 68 is 34, and I do half of 95 is 47.5. Add those together, and we get 81.5%. Now, again, if you wanted to, you could do 34 plus 34 plus 13.5, and it works. All right, this one, we have that we're less than 3, this little sliver over here, or we're bigger than 3. So Personally, what I would do is say, hey, 100% minus the 99.7 for the within 3. That's going to give us the 0.3% on either side. If you want to go up and add, you would add 0.15 and 0.15. Alrighty, your turn. So you should pause the video at this point, and you should try to answer these 3 questions on your own. All right, how was that? You totally paused, right? You didn't pretend again? No, you wouldn't do that to me again. All right, so you got this. So you know all these answers. I'm just going to go over it just to make sure that, we got the same thing. So here we have less than 2 standard deviations. So here's 2, and I'm going less than it. Lots of different ways. You can add the 2 numbers up top, so the 0.15 and the 2.35. Or you can say, hey, 95% is within 2. That means that 5% is outside of 2, and we only want half of that. So I divide that in half, and we're going to have 2.5%. And just to emphasize again, we only want half because this part over here is also outside of the 2 in either direction, right? So 95 is in between, and I have 5% total, and I only want half of that. So that's why I'm cutting it in half and getting the 2.5. All right, this guy, we got -2 all the way up to 3. I'm going to, again, split it down the middle. I'm doing half of 95 for the half of 2 standard deviations and half of 99.7 to give me that. And that's going to give me 97.35%. Or you can add up all those different numbers. So like 13.5 plus 34 plus 34 plus 13.5 plus 2.35, or whatever the numbers were. I'm not looking at them anymore, and I honestly don't have them memorized. All right, and the easiest question of the night, we are within 2, and we know that that's 95%. And I don't know why I said at night. It's hopefully daytime for you. It's definitely nighttime and past my bedtime for me, but that's what happens when you record a video and it deletes itself. Great. All right, we have one more example where we get to see how this stuff is applied to real life. Isn't that exciting? And we're almost at the 25-minute mark, so maybe I'll finish a little early. I don't know. We'll see. So first things first, we got men's heights are normally distributed. All heights are normally distributed, not just men's, everyone's. So we have 68 goes right in the middle, right? Because that's where our mean goes. Standard deviation of 2. That means that each one of these little tick marks is adding 2. Because each tick mark is 1 standard deviation away from the mean. And if our standard deviation is 2, then that means we go 2 away. And then I can go backwards, 66, 64, and 62. If I correlate that to our z-scores, those are z-scores of 0, 1, 2, 3, and then going backwards, -1, -2, -3. So let's do some math here. We want to find the percent of men that are over 72 inches tall, so over 6 feet. So we would say, hey, I want to find an x value that is over 72. And what I can do is turn that into a z-score and say, hey, that's really a z-score, and then 72 is associated with 2, if we look over on the little graph there. So I can say, okay, I'm looking for a z-score that is greater than 2, and we can just say, hey, that's this part right here. Lots of different ways of doing it. I'm just going to scroll up here and say, hey, it's going to be 2.5%, because we already figured out that less than 2 was 2.5, and since the graph is symmetrical, more than 2 is going to be the same. So I can say this is going to be 2.5%. The other way of thinking about it, right, is we can say, hey, 95 is going to be the total amount. We want the outsides, which is 5%, and then we want to cut that in half so that we only get each side of it, okay? Next, we have what is the probability that you find someone who is between 64 and 70 inches. When we look at our z-scores, 64 is -2, and 70 is 1. So we're looking for these values that go between -2 and 1. So this little region right here, if I were to shade it in. I don't really want to shade it in, so I'm going to get rid of that. All right, so when I'm looking at that, I like to split it up, right? So I'm going to do half of 95 for the 2, and then I'm going to add that with half of the 68 for the 1, and that's going to give me the 81.5%, which we've done already somewhere. I don't remember where, but we've done that one already. Next, we got probability that you are less than 62. All right, so as a z-score, that is going to be the probability that z is less than 3, which is going to be a pretty small number, right? That's going to be 0.15%. The way that I would do that is I would say, hey, 99.7% is within 3. And so that means 0.3 is outside. And then I want to cut that in half because I only want one side of it. So 0.15%. All right. Homework, practice. We got the comparing. We got find some z-scores. We got, this fun example with beagles. That sounds great. And then just some standard z-score practice. If you go to do the optional one, I just need to give you a warning here. You cannot do 9 right now. You need the calculator. It's because I didn't give us nice numbers here. You might notice a weak point of using the empirical rule is that if we were to have like a height of 67 in this men's height one, we can't calculate it. We can only calculate things that fall perfectly with a z-score of 1, 2, or 3. And so that's why we need to learn how to use the calculator, and ultimately something called a z-table is what we would have used back in the day, and I'll show you that. So I hope this made sense. I'm sorry I didn't get it faster than 25, but I guess that means I'm pretty consistent and I would have a low standard deviation. I hope you enjoyed that math joke. I will see you next class. Bye, friends.